Hello dear students, how are you? This is your instructor Musawir from UED Lahore New Campus. Today's topic is AM heterodyne and superheterodyne receiver. So what is this? It is just a technique of demodulation the AM signal. So let's discuss this. What is heterodyne receiver and what is superheterodyne receiver? A heterodyne receiver is nothing but just a simple demodulating technique. Means here we have the modulated signal, means the signal that is in the air, the modulated signal, the transmitted signal, and then by converting the modulated signal directly into the audio range, the audible signal means the signal that is connected to the speaker, and then we can listen it. So the you can say the turning, the sending of modulated signal directly into the audio signal, it is known as a heterodyne technique. So it is then done in heterodyne receivers. So what is a super heterodyne receiver? In super heterodyne receivers, we have the modulated signal, and then before converting into the audio signal, we have to convert this modulated signal into an intermediate frequency signal. So by just adding an intermediate stage, a frequency range which is known as intermediate frequency range. So by just adding this block, we can say that it is known as a super heterodyne receiver. Okay, let's analyze it. This is the block diagram of a heterodyne receiver. It is the modulated signal. Then you know that after catching the modulated signal from the air, we have to filter it, we have to amplify it. Okay. Then we have a balanced modulator. You know that in AM signals, balanced modulator is used to convert the signal into an upper band and into a lower band. So here comes the local oscillator wave. You can say that it is a tunable local oscillator, so we can adjust the carrier frequency from here. So this carrier frequency and this modulated wave, okay, they both, you can say, multiply with each other, or you can say they both will pass from a balanced modulator, and in the, you can say that in the output it will result the sum of this local oscillatory wave and this modulated signal, and there will be a difference of this local oscillator signal and this modulated wave. I hope you got that point, that there will be two results. One will be the sum of these two and the other will be the difference of these two. After it, we will just apply a low pass filter so that we can filter out our audible range, which is usually from 500 to 3500, approximately this is the range. So after filtration and amplification, we connect it to our speaker, and then we can listen what was in the modulated signal. This is the block diagram of a heterodyne receiver. In a super heterodyne receiver, we have an intermediate frequency range. What is this? Again, this is the modulated signal we have. We have filtered it so that we can, you can say, cancel out any noise and amplify it. Then we use a local oscillator here. We again use a balanced modulator. We will take the sum of these two, the difference of these two, and the result will be here. So at this point, why we are using this, you can say, this thing twice, once here and once here. This is done because of this filtration block. Why? Because in the previous one here we have only just one filtration, you can say, and you can say that the slope is a very large thing here, and we cannot clearly separate things. We cannot, you can say, perfectly precisely filter the things. To make it more precise, we use here an intermediate frequency range. This range is somehow, you can say, it is like that here the filters, obviously these are fixed filters, so these filters are actually, you can say that, filtering out the things in a more clear way. These are precisely filtering out just the message signal, because here actually the range is not high. In this case the filters have a very high range, you can say that from kilohertz to megahertz. But here in this case there is only a limited range, you can say only in kilohertz or only in megahertz. So if you have only things in kilohertz, you can design more precise filters, unlike here. So that's why this intermediate frequency range part is established here. Okay, I hope you got that point. So I will give you an example here. Let's suppose that here we have, you can say that, let's say 1 megahertz for instance. 1 megahertz, after filtration, you take the sum of these two, the product of these two. Here we have the sum 1 megahertz plus, you can take 545 kilohertz. So sum of these two, 1 megahertz and 545 kilohertz, and the difference of these two, 1 megahertz minus 545 kilohertz. So the result will be here. So one will be 1.545 megahertz, and the other will be, the difference will be 0.455 megahertz. So obviously you can say that here we have only a one range, which is megahertz, or you can take this in also kilohertz. One is 1545 kilohertz, and the other, means the difference here is 455 kilohertz. So if you have the units same, you can make more precise filters. So if you filter here, if you do this type of filtration, then the noise cancellation will be much better. So here at this point we are using a low pass filter. So at this point our signal will have a frequency of 455 kilohertz. Then we again used a balanced modulator and a frequency oscillator, so that the product will contain the sum of these two and the difference of these two. Obviously the difference will result audible range, and after filtration amplification we can connect it in speakers. In this part you can say that we have a direct thing. So the filter will have not clear results, you can say not precise results. You can take an example here. Let's say if we have 1 megahertz and 999 kilohertz, it is about 0.999 megahertz. So 1 megahertz plus 0.999 megahertz, it is equal to 1.999 megahertz. On the other hand, if you subtract 1 megahertz minus 0.999 megahertz, your answer will be 1 kilohertz. So where is 1 kilohertz and where is 1.999 megahertz? It is a huge difference. So if it is a huge difference, your filters will not act precisely. You can say you cannot design precise filters. So if you connect here speaker, you will get a lot of noise, and if you connect speaker here, the noise will definitely will be reduced. Okay, here we have the signal analysis. You can say a single sideband is here. You know what is a single sideband? I taught you. A single sideband is here, and here it is here it's a frequency domain. Its frequency spectrum. This is the first local oscillator wave. This one, the local oscillator. Tunable local oscillator means you can change the frequency of the local oscillator. And just for information, it can be built by using RC circuits or LC circuits, or you can say capacitor, resistive, and the combination of inductors. Okay, so you can take this single sideband modulated signal and this local oscillator wave to generate an intermediate frequency range, which is this one. After this balanced modulator, this will be the signal, and you can see clearly here that here we have two frequency ranges. One is this one. It is around, you can say, 2 2000 kilohertz, which is, you can say that, 2 megahertz, and it is around 455 kilohertz. And after filtration, this thing is around 455 kilohertz. Okay, and if you again use a local oscillator here to use a balanced modulator, the result will be a high signal and a low signal. You know, a balanced modulator creates the sum and difference, so the difference one will be our audible range, you can say our message signal. So after passing low pass, from a low pass filter, you can gain your original message signal, and here in this example it is 1 kilohertz. All right, okay, now we will move towards some experiments to see what will happen in real life things. Okay, so let's move here. Hey students, so this is the modulated signal, the signal which is present in the air. Okay, so you can see that this is the modulated signal we have, and we have to pass this signal from a balanced modulator to get the sum and the difference of two signals. So if I use here the balanced modulator, the result, it will be like this one. Let me show you. So this is the output of the balanced modulator. You know that this is the sum and difference of a message signal and the carrier signal. And message signal here, it is the modulated wave we have, and the carrier signal, it is from the local oscillator. So this is a balanced modulator, means a double sideband suppressed carrier. If I use a filter to extract a single sideband, it is usually the lower sideband. So the single sideband, it will look like this one. Okay, so this is the single sideband we have here. Okay, now as it is a superheterodyne, we have to again to pass it from a balanced modulator, and again the output of the balanced modulator, it will look like this one. So this is the output of the balanced modulator, and again we have to use a filter to extract the single sideband from here. Okay, so it will look like this one. All right, so you can say that after using specific filters, passing these from specific filters, we can extract our message signal, original message signal. It will obviously look like this one. Okay, so this will be our original message signal. I hope you got all the things about superheterodyne. Thank you for watching.